Good day, I'm Norman Wobbliger. Today we're going to introduce a fascinating structure in mathematics, which I like to call the successor-limit hierarchy. And we're introducing this in the context of these operations that we've been talking about in order to get bigger and bigger numbers. But in fact, the sort of structure of this successor-limit hierarchy transcends this particular application and has connections with other branches of mathematics. In particular, it's intimately connected with a branch of modern set theory having to do with ordinals. Now, I don't believe in modern set theory, and I don't believe in the usual theory of ordinals, but nevertheless, there is still some connection between what we're doing here, which is reasonably solid, and that may be more dubious theory of ordinals, and we'll talk about that later. We'll also see that this successor-limit hierarchy has a very profound application to our understanding of numbers and infinities, and also it turns out to infinitesimals. That's going to be down the road a little bit, but this is sort of laying some groundwork for that. So one starting point is this idea of a successor of an operation. So if we have an arithmetical operation, say circle cross, this could be an addition or multiplication or exponentiation or perhaps something quite different. It's an operation on natural numbers. We're going to define its successor, circle cross prime, in this fashion, which is now familiar to you, I hope. So m circle cross prime 1 is by definition m, and then there's an inductive or recursive definition defining m circle cross prime n plus 1 in terms of m circle cross prime of n, as well as the previous operation circle cross. Okay, so starting with addition, we've seen that this way we can build up first multiplication, and then exponentiation, and then this triangle operator, this square operator, and then higher operators by just taking the successor of the previous one. So then we have something that's a little bit outside of the successor operation, another way of getting a new operation. And this involves what we might call a limit, but it's quite a different kind of limit from the usual one studied in analysis. So we're using the same term, but maybe it would be better if we had some different term, but we'll use the same term, limit. And so we have this particular sequence of operations starting with star 1, or multiplication, and then star 2, which is exponentiation, star 3, which is the triangle operator, and so on. And from this sequence of operations, we conjure up a new operation called star infinity. And an alternate name for star infinity, one that we're going to use, is star n, where this n now is just the little letter n in the alphabet, and we're just going to employ it this way. You'll see the reason for that shortly. Okay, and what is the definition of this thing? Here's the definition. That if m and k are natural numbers, then m star n k is m star k k. In other words, we use this second number, the exponent, to determine the index of the star. So we're choosing the operation in this list, which is determined by this second number. There's a star k. And then we're just taking m star k k, the product of these two numbers with respect to this particular operation. So the k is somehow being used in two different places. It's a kind of a diagonal limit operation, as we've seen. Okay, so these are the two main ingredients, and now we are going to build up a hierarchy of operations. And this is a very interesting, powerful, and somewhat mysterious way of getting enormously big structures, enormously big numbers, enormously big operations. Okay, so the idea is that we have these two different ways of building new operations, successors and limits. And using those, we're going to build this successor-limit hierarchy of arithmetical operations. So if circle cross is pretty well any operation, we can always take its successor. Now limits is a little bit more subtle. If we have a particular sequence of operations that we've defined and put our finger on, then we can form this sort of infinite kind of limit of these sequences in exactly the same way as we've just done for the case of star 1, star 2, star 3. And of course, we'd like to be able to do this in a way that doesn't involve us having to get into this knotty realm of what we mean by infinite sequences. So what we're saying here is a kind of informal description of this process, and we are going to hope that down the road we can formalize it and make it very clear what's going on. So step by step, without actually invoking anything that's infinite. Now, before we get into that, I'd like to take a little bit of time just to explain a particular very special case. And that is a situation when we're looking at multiples or powers of 1, where we're multiplying two of our objects with one of our operations, and the first one happens to be 1. So let's have a look at the first star operator, star 1, which is multiplication. 1 star 1k, which is 1 times k, is actually k. That's actually rather special, because all of the other ones, we get something different. So 1 star 2k is 1 to the k, that's 1. 1 star 3k is 1 triangle k, that's 1 to the 1 to the 1 k times, that's also 1. And in fact, that's the pattern that happens from then on. So here's a little lemma, that if L is bigger than 1, then 1 star Lk equals 1 for any k natural number. This is a very simple looking formula, but it is rather subtle because there's actually two variables floating around here. There's the L, which we're assuming is bigger than 1, and of course a natural number, and there's also k. So we're asserting something being true for both L and k. So what we're going to do is going to prove this by induction. It's one of our first examples of induction. It's a rather sophisticated example, actually. So the idea is that we're going to, say, prove this for all L in the range we're interested in. So we're going to prove it true first for L equals 2. And we'll note that when L is equal to 2, then we've already looked at that case, that 1 star 2k is indeed equal to 1 for any k and natural number. So it's true for L equals 2. And now we're going to assume that it's true for some L, which is in the range that we're interested in. In other words, it's bigger than 1. And the aim is, by the end of the argument, we should have proven it for L plus 1. So it requires us to go from knowing that it's true for L to deducing that it's true for L plus 1. It's the basic inductive step that mimics our construction of natural numbers, starting with 1, or in this case 2, and proceeding one at a time to get wherever we want to go. Okay, so we're going to assume that this statement is true for some particular L. And now let's look at L plus 1. So the first thing to do with L plus 1 is to look at the special case when k equals 1. 1 star L plus 1, 1. Well, of course, that is equal to 1. Now, what about 1 star L plus 1, k plus 1? In order to see what this is, we use the definition of the recursive or inductive aspect of star L plus 1. This is by definition 1 star L acting on 1 star L plus 1k. That's our definition of how we go from star L to star L plus 1. Okay, so the claim that 1 star L plus 1k equals 1 for k in natural numbers, this is true by induction on k. Because, so let's say we're just interested in this claim that 1 star L plus 1k equals 1 for all k in n. L is now fixed. So it's true for k equals 1, and if it's true for k, then this was going to be equal to 1, and then this is going to be equal to 1, and then this is going to be equal to 1. So if it's true for k, then it's true for k plus 1. And so it's true by induction on k. All right, so we've proven that 1 star L plus 1k equals 1 for all k natural numbers. That's exactly what we wanted to do. We wanted to go from this statement to this statement, and we've done that, and so we've satisfied the inductive step for L, and so the lemma is true by induction on L. All right, this is a little bit sophisticated, so if it's a little bit complicated, have a think about it. It is a rather sophisticated notion of induction, even though the actual result is relatively simple. But we will be talking about induction some more. It's a very important kind of argument, and at least this is an introduction to it, but we will be talking about it on some other occasion as well. So this is just pinning down what happens to powers, or in fact multiples of 1 for any of our star sub k operations. All right, so let's build up this successor limit hierarchy. Let's begin. We've started with this basic sequence of operations. The star 1, star 2, star 3s, which ultimately came from addition by successor. And then we use this sequence to generate this star infinity, what we're calling star n. Now the possibility arises that we can take this star n, which is after all just an operation on natural numbers, and we can take its successor, because we can take the successor of any operation. So the successor of star n is defined the following way. And I'm going to now use m and k's instead of m and n's, because the n now is reserved for being this index underneath this operation. So previously in our various formulas we had m star something times n, okay? And now we're going to replace that with m star something times k. Okay, so m star n prime, the successor of this one, 1, is going to be m. That's always what we do. And here is the inductive step that defines m star n prime k plus 1 in terms of m star n prime k, as well as the previous operation, which is this star n. So there's a star n there. Okay, and now we're going to introduce some interesting notation for this successor of star n. We're going to give it another name. We're going to call it star n plus 1. All right, so star n plus 1 is by definition the successor of star n. Star n was defined in terms of the limit of these operations. Star n plus 1 is now defined as the successor of star n. So let's see if we can get our head around this new operation, star n plus 1, by just having a look at some simple examples. So 3 star n plus 1, 1, that's always 3. 3 star n plus 1, 2. All right, so we're just going to systematically look at the definition. This is by definition 3 star n times 3 star n plus 1, 1. So we lower this thing here by 1 there, and we lower this entry by 1 there. Now, what is 3 star n plus 1, 1? Well, 3 star anything 1 is equal to 3. So this becomes 3 star n, 3. And what is 3 star n, 3? Well, star n is the limit of star 1, star 2, star 3. And when we multiply 3 times star n, 3, what we have to do is we have to replace this n with this second entry, which happens to be a 3. So we get 3 star 3, 3. Now star 3 is our third exponentiation operator. That's our triangle operation. So this is just 3 triangle 3, which we know is 3 to the 3 to the 3, or 3 to the 27. So that's 3 star n plus 1, 2. And what about 3 star n plus 1, 3? Well, that'll be 3 star n, 1 less than this one, followed by 3 star n plus 1, 2, 1 less than this. Okay, now this is just what we've calculated. We've calculated that this thing here is 3 to the 27. So this is altogether 3 star n times 3 to the 27. Now the same kind of thing happens as before. This is a star n, that's a limit operation. So when we multiply this times this with respect to that, we have to replace the n with this second entry. So we get 3 star 3 to the 27 times 3 to the 27. Now this is a huge thing, because remember that when we start considering these various stars going past 3, 4, 5 and so on, we ended up with these towers of exponentials, and we had sort of a string of towers going this way, and then a bunch of braces of such strings going that way, and then another family of them going that way, and then another family of even bigger ones going down, and so on. So we keep on going this way, and then this way, and then this way, and then this way, sort of once for each one of these index values. So if we have 3 to the 27, we're doing that operation many, many times. So we get some huge array. This is some enormously huge number. Much, much bigger than z prime that we had a few videos ago. Okay, and let's just have a look at what the next one would be. 3 star n plus 1, 4. So again, by definition, that's 3 star n, and then multiplied by 3 star n plus 1, 3. That should be a 3. That too should be a 3. There we go. And so what we're getting here is what we've just calculated at the previous step, which is this 3 star 3 to the 27, 3 to the 27. And now we still have the star n here, so we have to replace the n here with this second sort of exponent. So here is 3 star 3 to the 27, 3 to the 27. That whole thing is the subscript under the star now. And then we have to, again, multiply that by the same thing here. So it's a similar kind of thing as we had here, except that the huge number that we obtained here is now the index for our star here, as well as being the exponent here, the second one. So this is vastly bigger than this one. It's almost incomprehensible how big this is. But these are still early days. This is still relatively modest compared to the things we're going to be seeing shortly. Great, so now we can go further. We can extend our hierarchy. We've had this row already, and now we can take the successor of star n to get star n plus 1. And there's no reason why we can now not take the successor of star n plus 1 to get star n plus 2, let's say. And the successor of star n plus 2 is star n plus 3, and so on. So we get a new sequence of operations sort of built from star n in the similar kind of way as these original ones were built from plus. And now a new idea suggests itself, that we can take the limit of this new sequence. So the sequence star n plus 1, star n plus 2, star n plus 3 also has a limit. And we're going to give that the name star 2n. Okay, so let's have a look at what that means in terms of a limit. The actual definition doesn't have any kind of limits involved. Okay, it's important to realize that we're not taking some infinite process here. We're not having to do something infinitely like a limit in analysis. So it's not a limit like an analysis. But nevertheless, we're still using that word, so confusion could possibly arise. So the definition here is very, very concrete. Star 2n. We're defining this operation very concretely. Here's a natural number m, here's a natural number k, and I'm telling you how to multiply m with k with this operation star 2n. Okay? And the definition is that what you do is you take this k and you replace 2n with n plus k. In other words, you go to the kth operation in this sequence that defines this limit, and you choose that kth one. So here's the first one, here's the second one, here's the third one. The kth one is star n plus k. So we take that kth operation that defined our limit, and we apply that operation to both m and k. So we've defined star 2n now in terms of a previous operation, but which previous operation it is depends on k. So for example, if we had to calculate 10 star 2n 3, then that's by definition 10 star n plus 3 times 3. And then we could try to simplify that because this is a successor. It's the successor of n plus 2. So we could write this as 10 star n plus 2 times 10 star n plus 3, and then subtract 1 here, 2. And we could then keep on going, try to unravel what this thing is. It might take us quite a long time to unravel what it is. Okay, so now an exciting prospect emerges, that we started with our first row to get our first limit, star n. These are all operations. And then we took successors of star n, we got a new sequence, and we took its limit, which we called star 2n. Now, of course, there's nothing to prevent us from taking successors of this one, and they are going to be called star 2n plus 1. That's the first one. And then the successor of that will be star 2n plus 2, and then star 2n plus 3. Now we have a new sequence of operations. We can take the limit of this sequence, and we'll get star 3n. And we can keep going here, right? Get the 4th row, 5th row, 6th row, and so on. So we're getting all these new limits. Let's actually circle them just to make it very clear. So these are kind of new kinds of operations that are different in character, essentially different in character from these ones. These ones are all successors. Each one of these is a successor of something that had gone before. These ones are not successors, they're limits. And notice that I have put a little colon beside them. That's some kind of notation that we could use to alert us to the fact that this thing here is actually a limit, not a successor. Okay, and now you might say, well, here's a lovely hierarchy, right? We've got this sort of potentially ongoing grid. We can just keep on adding more and more rows, and we can get bigger and bigger operations. Fabulous. That's good. But in this story, whenever you have some kind of pattern that you're comfortable with, you can go beyond your comfort zone. You can go to a next level. You may not want to, but you can. Okay. And in this case, going to the next level requires a shift of thinking. In fact, it almost always requires some kind of shift of thinking. You have to think in a little bit different way than you have been up till that point. So we're going to think a little bit differently. We're going to say, well, we've created these new kinds of operations. They are limit operations rather than successor operations. Okay, so now we have a new type of sequence. Namely, these green ones here, they themselves form a sequence of operations. They themselves form a sequence of operations. And so we can take their limit. We can take the limit of these ones. Previously, we've just been taking limits of things along rows. And now we're taking the limits of those rows and regarding them as a column, and we're going to take the limit of that. So here's star n, star 2n, star 3n. These can be used to generate a new operation called star n squared. Star n squared. And what is the definition of star n squared? Well, it's the same kind of thing that we've seen before. We always define a limiting operation on a sequence in the same way. So once we have our sequence clearly in mind, then the definition of the limiting operation is completely cut and dried. So m star n squared k. We're going to multiply m and k with this operation. So what do? Well, we regard this as being created in some limiting fashion from this sequence. And what we do is we take the kth element in this sequence. We look at the second exponent here, the second operand, and we take the kth element in the sequence. This is the first element, this is the second element, that's the third element, so the kth element will be star kn. And that's what we do to m and k. We multiply them with the operator star kn. That's already defined, it's already in existence. We're using it to multiply m and k, or maybe we should say exponentiate m and k, whatever. Okay, so this is quite interesting now. It's a new kind of limit. It's at some point kind of a higher limit than these ones because it's a limit of limits. So for example, we might now ask, what is 3 star n squared 4? Right? This is a number. These are numbers, and this is an operation, like exponentiation or triangle operation, but somewhat fancier, somewhat more complicated. The definition here tells us that we need to interpret this by thinking of replacing the n squared here with a fourth operation which defines this as a limit. So it becomes 3 star 4n 4. Alright, now it's an excellent exercise for you to pause the video and go off for a few hours. And a few hours is probably what you'll need, at least. And try to see if you can get your head around what's happening with this number. We want to evaluate this, or at least move towards evaluating, trying to figure out what does this number actually look like in some fashion or another. So we want to sort of strip away these various recursions and sort of reveal the number itself, although it'll be very big. So that's an excellent exercise to do this, so please have a go, and then you can compare with what I'm going to show you in a minute or two. All right? We'll see if we get something comparable. All right, so let's see if we agree on what we get here. And so I've done my best in trying to work this thing out, but I do admit that this kind of thing gives me a headache after a little while, and it's very easy to get confused. But nevertheless, you'll get the hang of it, I hope, and if I've made a mistake, then please correct me. Okay, but the point is we are still in the realm of somewhat realistic arithmetic here. At least in principle, we can unravel the things that we're talking about. These are very sophisticated operations. This is a very serious kind of arithmetic. But nevertheless, it does have a concrete aspect. It's just that the concreteness is blown out because of the complexity. You know, the complexity just skyrockets, and eventually it overwhelms us. And that's just the way it is. But nevertheless, still at every stage there's something concrete, at least potentially concrete, about what we're doing. Okay, so we're after 3 star n squared 4, a very modest looking arithmetical problem. And we've decided that that's 3 star 4n 4. Now, this thing here is also a limit. Okay, so we've already used the fact that n squared is a limit of these ones in order to go from here to here. Now, 4n is also a limit. Star 4n is the limit of star 3n plus 1, star 3n plus 2, star 3n plus 3, and so on. So when we evaluate this, because this is a limit, we have to basically sort of replace this thing with a fourth term that defines it as a limit. 4, because this entry is 4. So we have to look here and see which one's the fourth operation, and it is 3n plus 4. So this unravels to 3 star 3n plus 4 times 4. Now this is a successor. It's the successor of 3n plus 3. So the successor rule is that this thing here will be 3 star 3n plus 3, and then times the same operator, 3 star 3n plus 4, but with one less, with a 3 there. Alright, now at the next step, we're going to replace this thing here with something. So the 3 star 3n plus 4 becomes 3 star 3n plus 3. And then we get times 3 star 3n plus 4, the same one here, times 2, one less than that. Okay, we're just repeating this thing here, we're repeating this thing here. What about this thing here? So 3 star 3n plus 4, 2. Okay, that's going to be, again, by the same recursive rule, 3 star 3n plus 3 times 3 star 3n plus 4 times 1. But I'm not writing that down because I know that's equal to 3. I know that whenever we have something times 1, we're going to get the something. That is for all of the operations, except for, in fact, the original operation of multiplication, star 1. But for all the other ones, it works. All right, so this thing here reduces to 3 star 3n plus 3, 3. Okay, so notice that we've gone from here to here. I might just record that. It's useful to see that we've gone from here, this 3 star 3n plus 4, 3, has been sort of expanded to this more elaborate expression. We have 3 star 3n plus 3 times 3 star 3n plus 3, 3. Okay, now we need to unravel this one, this inside thing here. So this is just the same, that's the same. And now when we do the same thing here, we're going to get 3 star 3n plus 2, that one's going to drop, times 3, the same one, 3 star 3n plus 3, times 1 less there, which is 2. Then at the next level, this is all the same, that's all the same. This thing here, 3 star 3n plus 3, 2, it's the same kind of thing that we had up here. We're going to get 3 star 3n plus 2 times 3, because what's really here is 3 times, or 3 star 3n plus 3, 1, which is just 3. So we might observe here that, let's see, yeah, the same kind of thing that we had going from here to here is happening from here to here. So if we look at this thing here, that one there, that's getting replaced 2 lines down with this thing here. Okay, so you can see the same pattern going from here to here is going from this one to those ones. Okay, what happens at the next step? Well, this is the same, that's the same, that's the same. And now we're going to do the same thing that we just did in the previous ones, but I'm not going to go through all the motions. So you just take this thing here and you get 3 star 3n plus 1 times 3 star 3n plus 2, 2, and then you get 3 star 3n plus 1, 3 times 3n plus 1, 3. So we're going from here to here in the same kind of fashion as we had in the previous steps. Okay, so we're unraveling this thing, and so far it's sort of under control. Things are reasonable. We're getting more and more stars of stars of stars, so the length of things are going up, but the actual numbers involved so far are all manageable. It's because we started with relatively small numbers. It's because that 4 was relatively small. Okay, so here's what we have gotten on the previous page. We have 3 star n squared 4, and then we got this expression for it. And now let's look at the last term here. 3 star 3n plus 1, 3. So this is a successor. It's a successor of 3n. So it's 3 star 3n. And then we have to multiply that by 3 star 3n plus 1 of 2. And we've seen that's the same as 3 star 3n, 3. The same kind of two-step thing that we've done before. And now this is 3 star 3n. And this thing here is a limit. It's the limit of this particular sequence. So star 3n is the limit of star 2n plus 1, 2n plus 2, 2n plus 3, and so on. So when we want to evaluate this limiting thing, we have to replace this star 3n with the third operation that defines it in its limit. So we get 3 star 2n plus 3, 3, because the third one along here is star 2n plus 3. Okay, so now we have to unravel this with the successor story. So this becomes 3 star 2n plus 2, 3 star 2n plus 2, 3. Again, we're using 2 steps there, which is now familiar, I hope. And then at the next level here, we can do exactly the same thing as we did from here to here. So we get 3 star 2n plus 1 times 3 star 2n plus 1, 3. So things are becoming simpler in the sense that these operations are slowly moving down. They're decreasing. They're going down in our ladder. Okay, so what is this thing? Let's just have a look at 3 star 2n plus 1, 3. So the last term in all of this. So this is again a successor, so we can write it as 3 star 2n times 3 star 2n plus 1, 2, which is the same as 3 star 2n, 3. And so we get 3 star 2n times 3 star n plus 3, 3, because 2n is the limit of n plus 1, n plus 2, n plus 3, and we're asked to take the third element in that limit, which is n plus 3. Okay, so now let's take the last part of this, so 3 star n plus 3, 3. Just have a look at that. Things are getting simpler now, so we're moving towards having something where the last thing that we have in our bracket is actually something that we can write down in some fashion or another. Okay, so we've got 3 star n plus 3, 3, so that's a successor. 3 star n plus 2 times 3 star n plus 2, 3. Same kind of trick we've seen before. And then this thing here becomes 3 star n plus 1, 3 star n plus 1, 3. And now we have this last one. We're going to just peel this last one off. It's simpler than this one. It's 3 star n plus 1, 3. So that's 3 star n times 3 star n, 3. And now this 3 star n, 3 is something that we can touch base with, because we know star n is just the limit of star 1, star 2, star 3. So 3 star n, 3 is 3 star 3, 3. This is our familiar triangle operator. So we finally kind of gone down the ladder and found something that we can recognize. There is 3 star n, 3 to the 3 to the 3. There's 3 triangle 3. So 3 to the 3 to the 3, that's 3 to the 27, and here is 3 to the 27. Okay, so what this is telling us is that because this is a limit, that we have to replace the n here with 3 to the 27, so there it is there. So it's 3 star 7625597484987 times 3 to the 27, which is the same number. So now we are at something where we're touching base with the same kind of pictures that we used when we were drawing z prime some videos ago. But with z prime we had to kind of go across and then down and then across and then down about 5 times or something like that. Okay. Now we have to go across and down somewhat more times. Okay. We have to go across and down this many times. And each time we have towers of 3s. And then at the very end, the last tower has this many 3s in it. So this is inconceivably bigger than z prime is. Just, beyond anything that we can imagine. But this number, which we've finally kind of gotten some kind of picture of, now is just an ingredient, has to be then put back into wherever it came from. So it came from right here. Okay? So this humongous number now has to be put into here. And so now when you have to unravel these things here, you don't have 3s anymore like we've had pretty well all the way up till now. Now you have this humongous number there instead of the 3. Okay? That makes everything dramatically more complicated. So you have these trillions and trillions of steps to go down instead of just 3 steps like we've sort of had up till now. So you have to evaluate, put this thing into there, and then you have to evaluate this, and then you have to evaluate that. And once you've got that, then you plug all of that back into here, and then you have to evaluate this on that, and you take that and you plug that all back into here, and then you evaluate this on that, and then this on that, and then this on that, and that was all together what you have to put in here. And then you take this and you evaluate this, and then this on this, and then this on this, and then this on this. Pretty cool. We have completely lost track, except in this sort of formal way of this thing. It just completely overwhelms us. And this is only 3 star n squared 4. You can probably get an inkling that we are going to be going much further. Okay, we are going to be going much further, and This is, of course, sort of seemingly, in fantasy land, but it's in fact only partially in fantasy land. There's something very concrete about this. It's just that the concreteness is at a level of arithmetic which happens to be beyond us. It's like we're like amoeba or something, trying to understand a rocket ship. It's much more complicated than that comparison. But I remind you that my fellow mathematician colleagues seemingly have no problem with this kind of thing because they go to infinity all the time. They let n go to infinity. When you let n go to infinity in these various modern constructions, you are necessarily zooming past numbers like this. You just zip by them on your road to infinity. I hope you're starting to see the weight and the seriousness that these big numbers and the arithmetic with these big numbers imposes on us. It's a huge burden to honestly address what's going on here. And it becomes, I hope, very glib to make these pronouncements basically just by waving one's hand and making some phrase like, and now let's let n go to infinity. And now let's consider the infinite sum, n equals 1 to infinity, blah, blah, blah. Right? These are just really empty statements from a computational point of view. When you realize that the natural numbers really do have things like this. This is a natural number in the usual kind of scenario. And it's there. And it's just one of many, many which are even bigger. So next time we are going to carry on extending this remarkable successor limit hierarchy. And you might think, well, this is all just a crazy game. And to a certain extent, that's true. But we will also see later on that this successor limit hierarchy has a life independent of its role here in this super duper arithmetic. It can also be used in much more modest and tangible ways. In fact, eventually we're going to be looking at algebraic calculus, and we're going to be touching base with something called non-standard analysis, which is a kind of way of using infinitesimals to do calculus in a purely algebraic way. And when we do eventually get to that point, we'll see that exactly this successor limit hierarchy plays a very natural and useful and important role. So it's quite remarkable. So it's well worth you having some thinking about this hierarchy. And next time we're going to investigate it even further, and we're going to reveal more of its beauty and remarkable aspect. I hope you'll join me for that. I'm Norman Weilberger. Thanks for listening.